So last time we were talking about the different kinds of intermolecular forces, and now we're going to look at the process of vaporization. Vaporization is the transition from the liquid state to the gas state, and the opposite of that is condensation, the transition from a gas to a liquid. So here we have an illustration of a beaker full of water, and we have our little Mickey Mouse head water molecules in here. And you could envision these as being sort of like a mosh pit. It's a whole, it's a wild dance floor there at the molecular level. These guys are wiggling and jiggling, and they're moving, and there's a lot of activity going on there. So molecules near the surface can escape into the gas state, and then they're going to do what gases do, and they're going to fly around in straight lines until they bump into something. And if they happen to bump into something that directs them back towards the surface of the water, they'll get stuck again and get captured by the water. So the molecules leaving is called vaporization, and the molecules returning is called condensation. We've talked about how temperature is a measure of average kinetic energy. So if we look at this graph here, fraction of molecules with a particular amount of energy, at a low temperature, we're going to have a curve like this. Not all of the molecules have the same energy. Some have higher energy, some have lower energy. It's a distribution. If we increase the temperature, then the distribution spreads out and the average becomes higher. So what we're looking at here is it takes a certain amount of energy to break loose from the intermolecular forces that are holding the water together. And so this dotted line here is representing that minimum amount of kinetic energy. So the area under each of these curves represents the number of molecules that have enough energy to escape. So at a lower temperature, we have a smaller area, and at a higher temperature, we have a larger area. So at a higher temperature, evaporation happens more quickly. And that should make sense, because how do we dry our clothes? We put them in the dryer, right, which heats them and blows air through them. Why do we heat them? Because that makes them dry faster. Evaporation occurs more quickly at a higher temperature. An analogy I like to use for this is the children's game Red Rover. Have you guys heard of Red Rover? Ever played that? Red Rover, send Sally right over. Anybody? No? A couple people. They don't let kids play that anymore because you could get hurt. You could break your wrist. Yeah. But, what good is childhood if you don't break your wrist at least once, right? Yeah. Anyway, so the way Red Rover's played, you got two groups of kids. They line up across a grassy field, and they hold hands. And then the bossy one on one side says, Red Rover, send Sally right over. And so Sally has to come running across the grassy field and try to break through the hands of this other team. You can see why people could get hurt. So if you run fast, you're more likely to break through. If the people you target have weak grips, you're more likely to get through. And so I kind of envision the surface of the water here as a Red Rover line. And in order for these molecules to break through, they have to have enough kinetic energy, right? So it's only the ones with a higher kinetic energy that are going to break through. If you got somebody who's just walking really slow, they're just going to bump into the hands and get knocked back, right? And they have to walk of shame back across the field. So we can, I guess I got lost my train of thought there. So at a higher temperature, that corresponds to the children running faster at the Red Rover line, right? They've got more energy. And now more of them are likely to break through the Red Rover line, right? So we can increase the rate of evaporation by increasing the temperature. We can also increase that rate by increasing the surface area of the liquid. In order for molecules to break loose, they have to be able to get to the surface, right? I really don't like this little sentence here, so I'm just not even going to mention it. So if we think about, some liquid in a beaker or liquid in a shallow pan, right? Same amount of liquid. Well, the surface area of this water is much smaller than the surface area when it's in a big flat pan, right? So here we have more molecules that are close to the surface. And if they have enough energy, then they can escape. Here there are fewer molecules close to the surface, and so fewer molecules can escape. So if you have more surface area, you're also going to have faster evaporation. So you can think about this, imagine a cup of water, well, let's say 2 cups of water, and you take one and you spill it on the counter, right? And it spreads all over the place, and you leave the other one just sitting there. And you go to school, and you come back, 6 hours later. Which one is going to have evaporated more? The one in the cup, or the one that's spread out all over the place? The one that's spread out. Depending on how warm the day is, the spread out cup might have completely dried up by the time you get back. But it's going to take a long time for a glass of water to completely evaporate because the surface area is much smaller. The other thing that affects the rate of evaporation is the strength of the intermolecular forces. So in the Red Rover line, this is how tightly the children are holding hands, right? So if you've got, say, a team that's 6th grade boys, and they're like, right? And they're going to hold on really, really tightly, and then we won't do this sexist thing. We'll talk about kindergarten boys, right? And so then you've got the kindergarten boys, and these are just little 5-year-old kids, right? And they're trying, but they can't. Their grip isn't as strong. So people are going to be able to break through their line faster than through the 6th grader boys' line. Does that make sense? So stronger intermolecular forces evaporate slower. Weaker intermolecular forces evaporates more quickly. We have qualitative terms for this, volatile and non-volatile. So a volatile liquid is one that vaporizes easily. Non-volatile is one that does not vaporize easily. So if you think about something like nail polish remover or rubbing alcohol, like, maybe you need to get an immunization, they take a little piece of cotton and they rubbing alcohol in your skin to sterilize it, right, before they give you the injection. And it feels really cold, and you know it was wet, but you look over there, it's already dry, because it evaporates so quickly. But if you have a liquid like vegetable oil just really doesn't evaporate, does it? It is definitely non-volatile. Any questions so far? What if the beaker of water is thermally insulated? The particles that are evaporating are all of the ones that have the higher energy. If all the high energy ones are leaving, what does that do to the average energy of what remains? All the high energy ones leave. The average energy of the remaining ones then goes down, right? So what happens is, as the water evaporates, the remaining water cools down. It gets cooler. Vaporization is an endothermic process because the particles with higher kinetic energy are the ones that evaporate. And so they're taking their energy with them. The energy is leaving the system. And this is one of the reasons why we sweat. Sweating cools your body. Your body excretes sweat on your skin, which is mostly water, and then as that evaporates, it takes heat away and cools you. Okay? Yeah?
Why does your body also release salt, though? Salts?
That's a good question. Why does your body release salts also when you sweat? Well, your body, no, these are good questions. Your body doesn't have like areas that just have pure water, right? So all of the cells and everything, they're all solutions, and there's a lot of electrolytes in there. And so I think those electrolytes, the sodium chloride, potassium, magnesium. I think that's just coming out with the water. Yeah.
Not intentionally releasing.
I don't know that it serves any purpose. I don't know. Yeah. But the water evaporates and then the salts get left behind. And so if you've ever worked really hard on a summer day and you've got a dark shirt on, right, and it's just like drenched with sweat, and when it dries, it's all white and crusty looking, what the heck is, that's salt that came out of your body. And that's why if you're sweating profusely, you may need to drink something like Gatorade or something else with electrolytes, because you need certain amounts of salt in your body, not just sodium chloride.
What's the purpose of other salts though? Like why?
Well, sodium and potassium are the really important cations. There's sodium channels and potassium channels. And that's like totally out of my ballpark, right? But it's really cool. It's really cool. But your body needs those in order to function. So evaporation is an endothermic process, and this makes sense because if we think about, well, how could we make something evaporate faster? How could I make this wet towel dry faster, right? I could put it in the dryer and heat it up. I could stick it in the sun and heat it up. Putting energy into it causes it to evaporate faster. The opposite of evaporation is condensation. So if vaporization is endothermic, then condensation must be exothermic. A steam burn is caused by steam condensing into water on your skin, and you can get a much more severe burn from steam than from the similar temperature air that does not have a lot of water in it. Because as the water condenses, it releases a tremendous amount of heat. The energetics of vaporization and condensation have the effect of moderating climate. So when we have areas that have higher humidity, more water around them, we see that the average temperature variation is much lower than in places with lower humidity. So here I pulled some numbers from the internet, and this is averages for July, 1971 to 2000. In Fresno, average high 96.6 degrees Fahrenheit, low of 66.1 degrees Fahrenheit with a difference of 30.5 degrees Fahrenheit. That sounds about right. Sometimes it's even 40 degrees different between the high in the afternoon and the low at night. In San Francisco, the average high 68.2, low of 54.4. Yes, that's in July. And the difference is less than 14 degrees. Why is their temperature not fluctuating as much as ours does? Because San Francisco is surrounded by water, the bay and the ocean, right? And because of that, there's also more humidity in the air. Think lots and lots of fog. Right? But in Fresno, there's not a lot of water, not many bodies of water hanging around, and there's also very low humidity. So the evaporation and condensation of water moderates the temperature. Yeah, we do get we get tule fog in the winter, and if you pay attention, the days that are foggy, the temperature doesn't change much from high to low. It's the days that are clear and sunny where the temperature goes high and really low. Like, it could be 70 degrees during the day and like 40 at night, right? Easy for that to happen. So we can, of course, quantify the energy associated with vaporization. So this is called the heat of vaporization. And it's the amount of heat that's needed to vaporize 1 mole of liquid at its normal boiling point. So for water, we can write a chemical equation. Water in the liquid state going to water in the gas state, and this heat of vaporization is 40.7 kilojoules for every mole of water. This is always positive because evaporation is always an endothermic process. It depends a little bit on the temperature. This is at its normal boiling point. That's the heat of vaporization at the normal boiling point. If we look at water, normal boiling point is 100, and there's the heat of vaporization. If we do this at a different temperature, 25 degrees Celsius, which is room temperature, the heat of vaporization there is a little bit higher, but it's not a whole lot higher, not like you might expect. So it does depend a little bit on temperature. So we get 40.7 kilojoules per mole needed to evaporate 1 mole of liquid water. And so if we do the opposite process and condense 1 mole of water, then we'll see that the heat released is the same quantity, right? The sign is different because the energy is leaving the system. And so the heat of vaporization can be used as a conversion factor between moles of liquid and heat needed to vaporize or condense. So let's do an example here. Calculate the amount of heat in kilojoules required to vaporize 2.58 kilojoules of water at its boiling point. So we're given the value 2.58 kilograms of water, and we're asked to find the heat in kilojoules. Should we do it? Yeah.
The first train came at 1:12.
112, thank you.
Last night, really writing it down.
Last night we had 10 trains.
Yesterday?
But then I accidentally erased it before I could take a picture. Like, what? Anyway.
Behind, is that why you?
Is that clock behind? No, I just can't tell time.
There was 33 though when you okay.
Yeah, it was close enough. Nobody's gonna come and check our sig figs or anything. Okay, we're just rounding up. So what's happening here is we've got water, liquid water, that's evaporating, right? And delta H for that reaction is the heat of vaporization for water, which is 40.7 kilojoules per mole. And I don't expect you to know that number. You would go look it up. So we have 2.58 kilograms of liquid water. And we're trying to find out how many kilojoules of energy is required. So this really is a stoichiometry problem. And where do we start with stoichiometry problems? Grams to moles to moles to grams. Okay, I see a lot of students struggling with calculations, and you're not starting here. I really recommend just go back and start with grams to moles to moles to grams and adjust it for the particular problem. Here we're not given grams, we're given kilograms. Well, can we convert kilograms to grams? Sure we can. We're not trying to find grams at the end, we're trying to find kilojoules. When we're looking at energy, when we have this delta H, this value applies to each reactant and product. We don't have to go from moles of one thing to moles of another thing. We can just go from grams to moles and then straight to kilojoules. So we're going to start with 2.58 kilograms, and we're going to convert that to grams of water. We'll divide by kilograms, and then we're going to convert that to moles of water, dividing by grams, And then we can go straight to kilojoules dividing by moles. Because this term here gives us the relationship between kilojoules and moles. It's 40.7 kilojoules per 1 mole of water. How do we convert from kilograms to grams? What does kilo stand for? It stands for 1,000, or 10 to the 3. So in the bottom I have 1 kilogram. On top I'm going to write 1 times 10 to the 3, because that's what kilo stands for. And then how do we convert between moles and grams of water? Molar mass, right? We're not going to take time to figure out how to calculate that. We're just going to go there. So 2.58 times 10 to the 3 divided by 18.02 times 40.7. 5827.19 kilojoules. And if we look at the values that we've got, we're starting with a number that has 3 significant figures, and the heat of vaporization also has 3, so this should be rounded to 3 significant figures. We're rounding in the tens place. Be careful, because we can't round 5,827 to 583, right? So this would be 5830 kilojoules, or a safer thing to do is to put it in scientific notation first. I'm moving the decimal 1 to 3 places. 5.8. I want to keep this next digit, the 2, but the next digit is 5 or greater, so I have to round the 2 up to a 3. And then I don't have to worry about all the rest of them, times 10 to the, and I've moved it 3 places. Is 5,000 a big number or a small number? It's a big number, right? $5,000 is a lot of money. How does Mrs. K feel about big paychecks? I feel positive about them, right? So this is a positive exponent. I'm still occasionally seeing people get their exponents backwards, the sign. So that's our best answer there. Any questions? We talked about water evaporating from an open beaker. What if we have water evaporating in a sealed container? Here we have an Erlenmeyer flask with a stopper. So as the water evaporates, it gets into this space here, and it can be a gas, but it can't escape. So what happens is it bounces around up here and ends up condensing back in. So we have a rate of evaporation that's going to depend on the temperature of the water and on the surface area. And for this example here, the surface area and the temperature are not changing, so the rate of evaporation is not changing. The rate of condensation depends on how many gas molecules are up here. Initially, there are no gas molecules, and so no condensation can occur because there's nothing there to condense. As evaporation occurs, we get more gas particles here, and so we start to see some condensation. So now we got small arrows here. As we get more gas particles, then we're going to have more condensation. So the rate of evaporation stays the same. The rate of condensation starts at 0, and then it increases. At some point, they're going to be the same. And that's where we reach a state of dynamic equilibrium. The rate of evaporation equals the rate of condensation. So the rate of condensation depends on the concentration of gas molecules, which is equivalent also to the partial pressure of the gas molecules. So here's a graph showing the rate of these processes as a function of time. The rate of evaporation stays the same over time. The rate of condensation starts at 0 because initially there were no gas particles to condense. As evaporation occurs and we get more and more gas particles, then the rate of condensation increases, and at some point those become equal and then they remain equal. At that point, the concentration of gas particles or the partial pressure of the gas particles will stay the same. It's not a static system though, because we still have things evaporating and condensing. So it's a constant changeover of what molecules are there. But the number of them is the same, and that's called a dynamic equilibrium. So the partial pressure of the gas in that dynamic equilibrium is called the vapor pressure. The vapor pressure is going to depend on the strength of the intermolecular forces. If we have weak intermolecular forces, we're going to have a high vapor pressure because the rate of evaporation is going to be higher. If we have strong forces, it's hard for those particles to escape the liquid, and we're going to have a low vapor pressure. And this vapor pressure is what we were talking about when we talked about gases collected over water. What happens there? I'll draw a quick picture. We had a tube, and it was bubbling gas into this inverted beaker or cylinder, and so it's displacing the water. But here we have water essentially in a closed container, and so some of that water is going to evaporate, and it's going to establish a dynamic equilibrium, and so we're going to have water vapor there in addition to the gas that we're collecting. You had a question?
Do liquids always evaporate, even if, or I don't know how to say this, like, so is there a point at which they can't evaporate like, at all?
It's a good question. Is there a point at which they cannot evaporate at all? I'd have to say no in the strictest sense, because like when we talked about solubility, there are things that are practically insoluble, but if even one molecule dissolves, then there has been some solubility, right? So there are, at low temperatures, the amount of evaporation is going to be very, very slow, but we'll find out that even solids can have vapor pressures. Yeah. Other questions?
That's actually what I was going to ask next.
Yeah.
Solids can.
Yeah, solids can, they're not evaporating, they're subliming, but yeah, they can do that as well.
They're just skipping over liquid eventually.
Skipping the liquid, exactly. When we have a system in dynamic equilibrium that gets disturbed, that system is going to respond in a way to try to minimize the disturbance and return to equilibrium. And so hopefully you remember from Chem 3A, the Chatelier's principle. So here we have an equilibrium established between liquid and gas. Rate of evaporation, rate of condensation are equal. If we increase the volume of the gas by pulling up on this lid, the rate of evaporation is going to remain the same, but because the pressure, the partial pressure here, has gotten smaller due to the increase in volume, the rate of condensation is going to be smaller. And so since the rate of evaporation is larger, we're going to see more and more gas molecules appear until again it reestablishes that dynamic equilibrium where the rates are equal. If we then push down on this container and cause the volume of the gas to become very small, now the partial pressure here of that gas is much higher, and so the rate of condensation will be very large. And so that has the effect of then lowering the partial pressure until again they become equal. And so you can mess around with this all you want, but the partial pressure of that liquid in a closed container is going to be the same regardless of what you do to it. Well, yeah, it is very much like a piston, but here, instead of what's happening in here causing the piston to move, we are moving the piston and causing changes to happen in here.
Okay.
So like in an internal combustion engine, what you have is you have gasoline burning, which causes the formation of a lot of gases, which take up a lot of volume. And so those are going to push the piston up.
Okay. Is that so? In a piston, there's liquid. So the liquid's put into the cylinder, then the
No, in something like that, there really isn't liquid.
Oh, there's no liquid. It's just already in the gas.
Yeah, you're pretty much going to have gasoline in the vapor state, and then it gets a spark from the spark plug and causes a small controlled explosion, and then that pushes the piston up.
Okay.
Mm-hmm. Yep. I'm just going to skip that one. So the vapor pressure will be dependent on the temperature, because if we increase the temperature, we increase the rate of evaporation. We can also think of it this way: the vapor pressure will increase because more molecules have enough energy to be vaporized. So here we're looking at vapor pressure as a function of temperature. Here we've got water, and we see that as you increase the temperature of water, the vapor pressure goes up. Okay, so out here, a small change in temperature can cause a large change in vapor pressure. And we've got diethyl ether, we've got ethyl alcohol. This is ethylene glycol. This is a rather non-volatile liquid. Its vapor pressure does depend on temperature, but its vapor pressure is very small. That's the most common ingredient in antifreeze, radiator fluid. So what happens when a liquid boils? A liquid will boil at the temperature at which its vapor pressure equals the external pressure. So let's look at that for water. So here is normal atmospheric pressure, 760 torr, and water has a vapor pressure of 760 torr at 100 degrees Celsius. So what that means is that now even the molecules in the interior of the water have enough energy to get into the gas state and break free from their neighbors. So they're going to form these bubbles of water vapor, which then rise to the surface, and that's what we see. We see water boiling. That happens when you're at a temperature where the vapor pressure equals atmospheric pressure.
Before that point, it's just from the surface. They just come off
Yeah.
the surface. Okay.
Mm-hmm. Before it starts boiling, all the particles are escaping from just the surface of the water. So the boiling point then is going to depend on the external pressure. So normal boiling point is the temperature when its vapor pressure equals 1 atmosphere, which you would consider normal pressure, right? So that's 100 degrees Celsius for water. If we increase the pressure, say by using a pressure cooker or like an Instant Pot, right, that seals, as the water starts to boil, then it's going to build up pressure, and the water will actually boil at a higher temperature. If you are, say, a couple miles up the mountains and you're boiling water over your campfire, the water may be boiling at a temperature that's lower than 100 degrees. Well, if your water's boiling at less than 100 degrees, it's going to take longer to cook your food. If the water's boiling at higher, it's going to cook more quickly. And that's why pressure cookers can cook food faster than you can cook things in an open pot. So if we look at the temperature of water as we add heat to it, let's say we started around room temperature at 20 degrees, and as we add heat to it, the water's going to heat up, right? It's going to heat up until it gets to the boiling point. Once it starts boiling, the temperature doesn't change. If you add more heat, it only causes more rapid boiling. The temperature does not go up. Doesn't matter how much heat you put in there. So a pot of boiling water, 100 degrees Celsius. You don't even need a thermometer. If you want your water to boil at a higher temperature, then you have to have pressure above it. So the water will continue to boil without increasing in temperature until all the water has gone into the gas state, and then the temperature of the gas can go up. So we're supposed to use this figure to estimate the boiling point of water at an external pressure of 200 torr. Well, how do we do that? Well, we want to see what the temperature is at that pressure for the substance we're looking at. So here we're looking at water, and here's our 200 torr. So I'm just going to draw a line across to see where it runs into the curve for water. This could be a test question. You're like, well, I can't tell exactly what that is. Yeah, my line wasn't very straight. But look at the choices. I'm not trying to trick you here. Could that possibly be 0? Well, 0's over here. It's not 0. It's not 100. Is this 84? No, it's between 60 and 80, right? So 66. Any questions? I don't remember a lot from high school. I don't know about you guys, but it's been a lot more recent for you. But one of my very vivid memories of high school, honors chemistry class, and at the beginning of the class period, the teacher set up a big vacuum flask and had some water in it, and he had a vacuum pump, and it's going chug, 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 and just sucking the air out of this flask. And then he's telling us about who knows what. And after a while, the water in that flask started to boil. And then he made all of us come up and touch it with our bare hands. And the first person was pretty scared. I don't want to touch boiling water, right? That's hot. It wasn't hot. It was room temperature. It felt like touching the bench. Mind blown, right? You can make water boil at room temperature. You just have to get the pressure low enough. So room temperature, down here, you got to get the pressure really low. But you can do it. I'd love to be able to do that, but I don't have access to a pump like that. I don't know how he got one, but it would be really fun.
Boiling immediately if you put it in a vacuum?
A low enough vacuum, yeah. Yeah. If you get under the vapor pressure for that temperature, it'll boil. Yeah, it's crazy. Well, looking at that graph, let's look at it real quick again. These are not lines, are they? That relationship is not linear. It's an exponential relationship. This is the equation. And you can rearrange that equation into a linear form, and that's known as the Clausius-Clapeyron equation. Natural log of the vapor pressure is equal to negative heat of vaporization over R times 1 over the temperature in Kelvin plus the natural log of a constant. So we can graph the natural log of the vapor pressure versus 1 over T. So this is the y variable, and this is the x variable. And then wrong thing. This is the slope. So y equals mx plus b is the equation for a line, right? Do a lot of stuff like this in Chem 1B. So if you measure the vapor pressure at different temperatures, you can make a graph and find out what the heat of vaporization is. Yes? We won't use this particular equation on the test because in order to use it, you have to make a graph, right? And we're not going to mess around with that. But I'll show you a slightly different form that definitely could show up on the exam. So this is an example of a Clausius-Clapeyron plot. So we're graphing natural log of pressure as a function of 1 over the temperature in kelvins. So we've done graphing in lab. You can graph this on Excel, and you can have it do linear regression and tell you what the equation for the line is. And so it'll tell you, well, the slope for this line is negative 3,478 Kelvin. Well, that slope is equal to negative delta H over R. So we can rearrange that. Delta H then is equal to negative slope times R. The R that we're using here is the 8.314 joules per mole Kelvin because we're dealing with energy. So we're going to end up with a value of joules per mole. And so you can calculate the heat of vaporization that way. I'm not going to do this example in class because it would require getting into Excel. But there might be a homework problem like this. So here we have the data, temperature, and pressure. To make that graph, we have to do a little bit of calculation. So we need to have 1 over the temperature. So that would be 1 divided by 255, or 0.00392. And then we would want the natural log of the vapor pressure. So that natural log of 11.3 is 2.425. And so you would do those calculations and then graph the data. In the video tutorial for one of our early labs that involved graphing, it shows you how you can set these up as equations in Excel and just type the equation in once and then copy it down and it'll do all those calculations for you. It's very cool. So this is what's called the 2-point form of the Clausius-Clapeyron equation. And this is a little more useful for our purposes. So this will predict the vapor pressure at a given temperature, provided that we know the heat of vaporization and the boiling point of whatever the substance is. Or if we have vapor pressure at 2 different temperatures, then we could solve for delta H. So here's an example of that. Propane has a normal boiling point of negative 42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What is the vapor pressure of propane at 25 degrees Celsius? So we've got some numbers here. And we've got a question with the vapor pressure. So this is going to use that 2-point form of the Clausius-Clapeyron equation, which you do not need to memorize. That would be given to you. Well, we see that we've been given 2 temperatures, right? So let's call the first one T1. And let's call the second one T2. We cannot use Celsius here, because if we use Celsius, we might very well have a place where we have 1 divided by 0, and that's undefined. Right, so we have to use Kelvin because the Kelvin scale doesn't have, we're not going to run it to 0. So if we change these into Kelvin, this would be 231.15 Kelvin, and this would be 298. Oops. Kelvin. And they're asking, what's the vapor pressure at this temperature? Well, we decided we were going to call that temperature 2. So then what we're looking for is pressure 2. And we were told that the heat of vaporization was 19.04 kilojoules per mole. And we can look up and see that R is equal to 8.314 joules per mole Kelvin. So, oops. We're trying to find P2, but what are we missing? What's P1? It doesn't say. But it says this is the normal boiling point. What's the pressure at the normal boiling point? It's normal pressure, 1 atmosphere, which would be how many torr? 760? So P1 must be 760 torr. And that's kind of the trick to this question, because they don't just come out and tell you that's the pressure. So we can plug all these things into the equation. This is one of those equations that is pretty ugly to rearrange and solve for the desired variable, right? To rearrange this and solve for P2 is going to be pretty ugly and make most of you crazy, right? Just be super, super frustrating. So this is one where it's better to just put the numbers in and then deal with it that way. So the natural log of P2 divided by 760 torr is going to be equal to 19.04 kilojoules per mole divided by 8.314 joules per mole Kelvin times 1 over T2, which is 298.15 Kelvin, minus 1 over T1, which was 231.15 Kelvin. Before we calculate anything, let's look at the units. So I've got moles, and I've got kelvins, and that's all nice, but I've got kilojoules and joules. That's not going to be okay. So I need my delta H here to be in joules per mole. And so that's where we can use that little shortcut thing again and say, well, kilo means times 10 to the 3. So I can convert it to joules that way. Now, the right side here, you can do on your calculator, and please do not try to find the lowest common denominator for those fractions. That's just going to be super ugly. Use your calculator. It can handle this. So I've got 19.04 times 10 to the 3 divided by 8.314 times, and then I'm going to open parentheses, and I've got 1 divided by 298.15 minus 1 divided by 231.15, close the parentheses and press equals. And so that's going to give me negative 2.22639. And more digits are not going to hurt anything. But if you round that to negative 2, you're going to have some problems. How do we, or what's the opposite of natural log? E to the x is the antilog, right? So if I do the antilog of both sides, e to the x and natural log are going to cancel out, and so this side becomes P2 over 760 torr. And over on the right, that's e to the negative 2.226399 is 0.107916, blah, blah, blah. So now I can multiply both sides by 760. And I did something wrong, because I'm getting 82, which is not the correct answer. What did I do? I'm just going to run it through my calculator again. And I'm getting the same answer. No e to that. Getting the same answer. Dang. Anybody have a clue what I'm doing wrong? Thank you. Yes, I'm missing a negative. There's a negative here. Yep. So this has to be negative, which makes this positive. So I've got e to the positive 2.226399, which is 9.266437 times 760. There we go. Thank you for your assistance. 7042.49. So that should probably have 3 sig figs. So we would say that's 7.04 times 10 to the third torr. Any questions? It's kind of a challenging math problem for most students. Yeah?
Why do we do this in torr, not atmospheres?
You could do this in atmospheres. You definitely could. You can use any pressure unit you want here as long as P2 and P1 are in the same unit. The reason I use torr is because the book gives the answer in torr. Yeah. But yeah, you could use even inches of mercury or PSI, doesn't matter. Yeah, great question. Anybody else?
When you said they have to match the torr and inches of mercury are the same, or no, millimeters.
Torr and millimeters of mercury are the same. So this is a great problem to be able to do, but if you look at that and go, oh, just skip that one, okay? Being able to do energy calculations, stoichiometry calculations, those sorts of things are much, much more important than this, okay? We talked about heating a liquid or evaporation in an open container. We talked about evaporation in a closed container. What if we have evaporation in a closed container and we're heating it? So here's a picture. There's gas here and there's liquid is here. So we have 2 states. As we heat this up, the liquid becomes less dense and the gas becomes more dense, and at a certain temperature, these merge into one state, which is called a supercritical fluid. And that state will occur anywhere at any temperature above the critical temperature. So the critical temperature, Tc, is the temperature at which a supercritical fluid forms. Above that temperature, you cannot have a liquid. The pressure that occurs at that transition is called the supercritical pressure. So why do we even talk about these? Supercritical fluids are actually really, really useful solvents. Supercritical CO2 can be used to decaffeinate coffee. So you can remove the caffeine without removing the compounds that give the coffee the flavor that you like. And when the process is over, it leaves behind no harmful residues because all the CO2 just evaporates.
That's how they make decaf?
That's one way, yeah. Mm-hmm. Because you think about, okay, so you've got these coffee beans, right? Because you can decaffeinate coffee beans. You don't have to do the ground coffee. How do you get the caffeine out without getting the other stuff out? It's a puzzle. Supercritical CO2 can do that.
But so it's in its gas form or it's liquid form? Sorry.
It's a supercritical fluid.
Oh, so it's not.
It's neither or both, depending on your point of view. Yeah. Yeah, it's crazy.
In between.
Because you can't get the caffeine to dissolve in a gas. But if you stick the beans in a liquid, then you're going to have some problems. Anyway, that's the application.